Welcome to this coding walkthrough. In this session, we're tackling LeetCode problem number 1854, maximum population year. This problem challenges us to determine the year with the maximum population based on given birth and death year intervals. Let's dive in and explore the problem, approaches, and solutions together. In this problem, you're given a 2D integer array called logs, where each entry represents the birth and death years of a person. Specifically, for the ith person, logs I equals birth_I, death_I means that this person was born in birth_I and passed away in death_I. The key detail to note is that a person is considered alive during the years starting from their birth year, birth_I, up to 1 year before their death year, death_I. For example, if someone is born in 1993 and dies in 1999, they are alive from 1993 to 1998, inclusive. The goal is to determine the earliest year that has the maximum population, which is defined as the highest number of people alive during any given year. The output of the problem is an integer that represents the earliest year with the maximum population. To understand how this works, let's consider an example. Suppose the input is logs equals 1993, 1999, 2000, 2010. Here, the first person is alive from 1993 to 1998, while the second person is alive from 2000 to 2009. We can calculate the population for each year. From 1993 to 1998, there's only one person alive, so the population is 1. From 2000 to 2009, the population is also 1 because the second person is the only one alive during those years. Now, let's look at the remaining years to finalize the population counts. In 1999, no one is alive since the first person has already passed away, so the population is 0. Similarly, in 2010, the second person is no longer alive, and the population again drops to 0. By analyzing the population counts, we see that the maximum population is 1, which occurs in multiple intervals, 1993 to 1998 and 2000 to 2009. However, since we are tasked with finding the earliest year with the maximum population, the answer is 1993. Let's look at another example. Suppose the input is logs equals 1950, 1961, 1960, 1971, 1970, 1981. Here, the first person is alive from 1950 to 1960, the second person from 1960 to 1970, and the third person from 1970 to 1980. Breaking it down by year, from 1950 to 1959, only the first person is alive, so the population is 1. From 1960 to 1969, both the first and second persons are alive, giving a population of 2. Similarly, from 1970 to 1979, the second and third persons are alive, keeping the population at 2. Finally, in 1980, only the third person is alive, so the population drops back to 1. By analyzing these population counts, we find that the maximum population is 2. This occurs between 1960 to 1969 and 1970 to 1979. Since we need the earliest year with the maximum population, the answer is 1960. Now, consider a simpler example with logs equals 2000, 2010. Here, there's only one person, who is alive from 2000 to 2009. The population is 1 during this interval, and 0 in 2010. Since the maximum population is 1, the earliest year with this maximum population is 2000. Finally, let's discuss some important constraints and edge cases. The total number of entries in logs will be between 1 and 100. The birth and death years will always fall within the range 1950 to 2050, and the birth year will always be strictly less than the death year. For edge cases, consider when there's only one person, the result will simply be the birth year of that person. In cases where no lifespans overlap, the result will be the birth year of the earliest person. Additionally, if multiple years share the same maximum population, you must return the earliest year. This ensures the solution is both correct and consistent across all scenarios. To start, let's consider the brute force approach. The intuition here is straightforward. For each year within the range of the minimum and maximum birth or death years, we count the number of people alive during that specific year. This involves checking every person in the logs to see if their lifespan overlaps with the year in question. Once we calculate the population for each year, we update the maximum population year whenever we find a higher count. While this method is simple and easy to understand, it's not very efficient. The time complexity is O, n asterisk y, where n is the number of people and y is the range of years. Essentially, this nested iteration makes the brute force approach impractical for cases with a large number of years or people. On the positive side, it has a low space complexity of O(1), but the trade-off in performance makes it unsuitable for larger inputs. Now, let's explore the optimized solution using the difference array, also known as the sweep line technique. The key observation here is that a person's contribution to the population is limited to the range between their birth and just before their death year. Instead of calculating the population year by year for every individual, we use an array called delta to record population changes. For each person in the logs, we increment the value at their birth year in the delta array and decrement the value at their death year. Once we have this delta array, we compute a running sum to determine the population for each year efficiently. By doing so, we can also track the year with the maximum population during the running sum calculation. This method significantly reduces redundant computations. The time complexity is O, n plus y, where n accounts for updating the delta array and y covers the running sum calculation. However, it does require O, y, space for the delta array, which can be a limitation if the year range is very large. Overall, this approach is highly efficient and scalable for most practical scenarios. Alternatively, we could use a sorting-based approach. Here, we first transform the input logs into events, where each birth is represented as year plus 1 and each death as year minus 1. These events are then sorted by year, with births taking precedence over deaths in case of ties. Once sorted, we process the events sequentially, maintaining a running count of the population. As we traverse through the events, we track the maximum population and the year when this occurs. The time complexity of this method is O, n log n, dominated by the sorting step, whereas the space complexity is O, n, for storing the events. While this approach is elegant and avoids the memory overhead of the delta array, the logarithmic cost of sorting might make it less appealing for scenarios with small year ranges. Still, it's a clean and effective solution, particularly when memory usage is a concern. With these considerations in mind, we chose the difference array, or sweep line, approach as the preferred strategy for this problem. The primary reason is its efficiency in both time and space under the given constraints. By focusing only on the changes at specific years, births and deaths, we eliminate redundant calculations and streamline the process. The running sum not only simplifies the population calculation but also makes it easy to track the maximum population year. Additionally, this method is straightforward to implement, reducing the likelihood of errors compared to the sorting approach, which requires careful handling of ties. While the sorting method is attractive in its elegance, the added complexity and sorting overhead are unnecessary here. The brute force approach, though intuitive, is simply not scalable. The key insight that solidified our choice was recognizing that we don't need to compute the exact population for every year up front. Instead, tracking changes using a difference array is enough to efficiently solve the problem. The problem we're solving here is to determine the year with the maximum number of people alive, given a list of logs where each entry specifies a person's birth year and death year. It's important to note that a person is considered alive from their birth year up to the year before their death, inclusive. To solve this, we use a sweeping line algorithm, which is a combination of sorting and prefix sums. The first step is input parsing, where the logs are processed as an array of birth, death pairs. Each birth year marks the beginning of a person's life, increasing the count of people alive, while the death year marks the end, decreasing it. Next, we consolidate these into two types of events, a birth event, which adds 1 to the count, and a death event, which subtracts 1. These events are represented as tuples of the form, year, effect, where the effect is either +1 for births or -1 for deaths. This setup prepares the data for efficient processing in subsequent steps. Once we have the events, the next step is to sort them. Sorting ensures that we process events in chronological order. If two events occur in the same year, we prioritize death events over birth events. This ensures accuracy in cases where someone dies the same year someone else is born, as the person who died should not be counted as alive for that year. After sorting, we implement the sweeping line algorithm. we initialize a counter, current_alive, to track the number of people alive at any given time, and two variables, max_alive and max_year, to record the maximum number of people alive and the corresponding year. As we iterate through the sorted events, we update the current_alive counter based on the effect of each event. If a birth event is encountered, current_alive increases. If it's a death event, current_alive decreases. After each update, we check if the current count exceeds the maximum observed so far. If it does, we update max_alive and record the year in max_year. At the end of this process, max_year holds the answer, the year with the maximum number of people alive. This method is both efficient and intuitive because it focuses only on the years where changes occur. Instead of iterating over every possible year in the range, which can be computationally expensive for large datasets, we limit our attention to birth and death years. Sorting the events ensures chronological processing, and prioritizing death events in the case of ties prevents double counting. The efficiency of this approach lies in its time complexity. Sorting the events takes n log n, where n is the number of events, and the sweeping line algorithm itself has a time complexity of n. This makes the overall complexity n log n, which is efficient given the nature of the problem. By combining event-based processing with sorting and a linear sweep, we achieve an optimal solution that balances clarity and performance. To implement this algorithm, we use specific data structures and variables for tracking. The events are stored as an array of tuples, where each tuple represents a birth or death event in the form, year, effect. This structure allows for easy sorting and processing. Additionally, we maintain three key variables, current_alive, to track the current count of people alive as we process events, max_alive, to store the maximum count encountered, and max_year, to record the year corresponding to max_alive. These variables work together within the sweeping line algorithm to ensure we capture the correct year with the maximum population efficiently and accurately. There are a few edge cases to consider to ensure the algorithm handles all scenarios correctly. One such case is when a birth and a death occur in the same year. By prioritizing death events during sorting, we ensure that the person who dies is not counted as alive for that year. Another scenario is when all lifespans overlap in a single year, creating a peak population during that year. The algorithm correctly identifies this peak by processing events in order. Finally, in cases where no lifespans overlap, each person is alive during distinct years. The algorithm still handles this correctly, as each birth and death event is considered individually, ensuring the result is accurate regardless of the input structure. To visualize how the algorithm works, let's consider a specific example. Suppose the input logs are 1900, 1950, 1920, 1930, 1940, 1960. First, we create events. Birth events are 1900 plus 1, 1920 plus 1, 1940 plus 1, and death events are 1950 minus 1, 1930 minus 1, 1960 minus 1. After combining and sorting these events, we get 1900 plus 1, 1920 plus 1, 1930 minus 1, 1940 plus 1, 1950 minus 1, 1960 minus 1. Now, processing these events step by step, we track the number of people alive. At year 1900, one person is alive. By 1920, the count rises to 2, which becomes the maximum so far. At 1930, it decreases to 1, rises to 2 again by 1940, and then gradually decreases to 0 by 1960. The maximum population occurs in 1920, making it the year with the most people alive. This step-by-step processing illustrates the algorithm's accuracy and efficiency in identifying the correct result. This Python implementation solves LeetCode problem number 1854, maximum population year, using an efficient approach based on the prefix sum method. The problem requires determining the year within the range 1950 to 2050 that has the maximum number of people alive, based on a list of birth and death years. Step-by-step explanation asterisk. 1. Initialization asterisk. A list year underscore population of size 101 is initialized to 0. Each index in this list corresponds to a year from 1950 to 2050, where year underscore population 0 represents 1950, year underscore population 1 represents 1951, and so on. 2. Population change tracking asterisk. For each log entry, birth, death, we increment the value at year_population, birth 1950, to account for a person being born in that year. Similarly, we decrement the value at year_population, death 1950, to reflect the fact that the person is no longer alive starting from the death year. This step ensures that the population changes, births and deaths, are recorded effectively without explicitly iterating through all the years for each log entry, which would be computationally expensive. 3. Prefix sum calculation asterisk. The next step involves calculating the prefix sum of the year_population array. This running sum is stored in current_population to determine the total population for each year. As we iterate through the years, we check if the current_population exceeds the max_population recorded so far. If it does, we update max_population and record the corresponding year as max_year. 4. Result asterisk. Once the iteration is complete, the max_year variable holds the year with the maximum population, which is returned as the result. Efficiency asterisk. The solution runs in O, n plus y, time, where n is the number of log entries and y is the range of years, 101 in this case. This is significantly faster than a naive approach that involves iterating through all years for each log entry. The space complexity is O, y, as we use an array of size 101 to track population changes. This approach ensures correctness and handles edge cases such as overlapping lifespans or multiple people sharing the same birth or death year. Here, we begin by defining the maximum population method, which takes a 2D array called logs as input, where each subarray represents a birth year and a death year. To keep track of population changes across years, we initialize an array year population of size 101, corresponding to the years from 1950 to 2050. Each index in this array represents a specific year, with index 0 mapping to 1950. Next, we iterate over the logs array. For each birth year, we increment the corresponding index in year population, and for each death year, we decrement the index. This ensures that we account for population increase at birth and decrease at death. By the end of this loop, the year population array holds the net population changes for each year. Now, to determine the year with the maximum population, we calculate a running total of the population for each year using a prefix sum. We initialize variables for tracking the max population, the max year, and the current population. As we traverse the year population array, we update the current population by adding the value at the current index. If this running total exceeds the recorded max population, we update both max population and max year. Finally, once the loop completes, we return max year, which represents the year with the highest population. This approach efficiently calculates the result in a single traversal after processing the input, making it optimal and easy to understand. In this problem, our goal is to find the year with the highest population between 1950 and 2050, given a list of birth and death years for multiple individuals. It's important to note that a person is only counted as alive from their birth year up to, but not including, their death year. To solve this, we start by initializing an array called year_population with 101 zeros, where each index corresponds to a year between 1950 and 2050. We then iterate through each log in the input. For the first log, 1993-1999, we increment the population at the index corresponding to 1993, which is 1993-1950 equals 43, and decrement the population at the index corresponding to 1999, index 49. Similarly, for 2000-2010, we increment the population at index 50 and decrement at index 60. Finally, for 1990-1995, we increment at index 40 and decrement at index 45. This approach allows us to efficiently record the population changes over time without directly iterating through all years for each log. Once we've recorded all the population changes in the year_population array, the next step is to calculate the cumulative population year by year using a prefix sum approach. Starting with a current_population of 0, we add the value at each index of the year_population array to current_population as we move through the array. At each step, we check if the current_population exceeds the maximum population encountered so far. For example, at index 40, which corresponds to the year 1990, the population becomes 1. At index 43 for the year 1993, it increases to 2, which is the new maximum. Later, at index 50 for the year 2000, the population drops back to 1. From this process, we determine that the year with the highest population is 1993. Now, let's consider a different example with logs: 1950, 1960, 1960, 1970, 1970, 1980. We start by initializing year_population again as an array of 101 zeros. For the first log, 1950, 1960, we increment the population at index 0, year 1950, and decrement it at index 10, year 1960. For the second log, 1960, 1970, we increment at index 10 and decrement at index 20. Similarly, for 1970, 1980, we increment at index 20 and decrement at index 30. After applying these changes, we calculate the cumulative population using the prefix sum method. At index 0, corresponding to the year 1950, the population is 1, which is the highest. At index 10 for the year 1960, the population remains 1, but it doesn't exceed the previous maximum. Therefore, the year with the maximum population in this example is 1950. In this third example, the logs are 2020, 2025, 2022, 2023. We initialize the year_population array as before. For the first log, 2020, 2025, we increment the population at index 70, year 2020, and decrement it at index 75, year 2025. For the second log, 2022, 2023, we increment at index 72, year 2022, and decrement at index 73, year 2023. We then compute the prefix sum to find the cumulative population year by year. At index 70 for the year 2020, the population is 1. At index 72 for 2022, the population rises to 2, which becomes the new maximum. Therefore, the year with the highest population in this case is 2022. To summarize, the solution involves processing the input logs to record population changes in an array, and then using a prefix sum to compute the cumulative population for each year. For the three examples provided, the results are as follows. In example 1, the year with the maximum population is 1993. In example 2, it is 1950. In example 3, the year with the highest population is 2022. To analyze the time complexity of this solution, let's break it into 3 distinct steps. First, we initialize the year_population array, which represents the years from 1950 to 2050. This array has a fixed size of 101, and initializing it with zeros involves a constant amount of work, 101. Since this operation doesn't depend on the size of the input, it simplifies to 1. Next, we process the logs array. Each log contains a birth year and a death year, and for every log, we increment and decrement the respective indices in the year_population array. Since there are n logs, this step involves n iterations, and each iteration takes constant time. Therefore, this part of the solution takes n time. Finally, we calculate the prefix sum to determine the maximum population and the corresponding year. This involves a single traversal of the year_population array, which is fixed at 101 iterations, contributing another 1 time. These steps collectively form the basis of our time complexity analysis. When we look at the total time complexity, the dominant term comes from processing the logs array, which is n. The other steps, including initializing the array and calculating the prefix sum, are constant time operations and do not grow with the size of the input. Therefore, the overall time complexity of the solution is n. Now, examining the space complexity, the year_population array is of fixed size, containing 101 elements. Regardless of the number of logs, this array requires 1 space. As for the logs array itself, it is part of the input and does not count as extra space for our algorithm. The additional variables used in the solution, such as max_population, max_year, and current_population, also consume a constant amount of space. Altogether, the solution uses 1 space beyond the input, making it very efficient in terms of memory usage. Summarizing the space complexity, the algorithm only requires a constant amount of extra space, 1, independent of the size of the input. This is because the year_population array and the other variables do not scale with the number of logs. Comparing this approach to a brute force solution highlights the advantages of the optimization. A naive approach might involve iterating through each year from 1950 to 2050 and counting the number of people alive during each year by checking all n logs. This would result in a time complexity of O(101*n), which simplifies to O(n), since 101 is a constant. While the space complexity for the brute force approach would still be O(1), the current solution significantly reduces the number of operations per year. By using the prefix sum technique, we calculate population changes in a single pass, achieving the same O(n) time complexity but with a more efficient process. For this problem, the best, average, and worst-case scenarios all result in the same time complexity of O(n). This is because the algorithm's runtime depends linearly on the number of logs, and every log must be processed regardless of the input configuration. Mathematically, the big O analysis is as follows. The initialization of the year_population array takes constant time, O(101), which simplifies to O(1). Processing the logs array requires O(n) operations, as each log involves two constant time updates. Finally, calculating the prefix sum and determining the maximum population involves another O(101) operations, which is also O(1). Adding these together, we get O(n) plus O(1) plus O(1), which simplifies to O(n). In terms of space, the fixed-size year_population array dominates the usage, resulting in O(1) space complexity. This efficient use of time and space makes the solution optimal for the given problem constraints. Here, let's address some common mistakes that often trip up programmers when solving the maximum population year problem. The first mistake involves iterating over an incorrect range of years, which typically happens due to off-by-one errors. For instance, the problem might specify that a person is alive during their birth year, but not their death year. Misunderstanding this can lead to inaccuracies, especially at the boundary years. Always double-check whether the range is inclusive or exclusive for birth and death years. The next issue arises from using an inefficient brute force approach. If you iterate through every year and then count the number of people alive by checking every birth and death event, the complexity becomes O(y*n), which is inefficient for large ranges of years. Instead, optimized techniques like prefix sums or event sorting are better suited. Lastly, some developers assume that the input data is sorted, but birth and death years are often unsorted. Relying on this incorrect assumption can lead to invalid results, especially when implementing more advanced methods like event sorting. Sorting the data first is an essential step to ensure correctness. Another common pitfall is misunderstanding edge cases, particularly around whether people are considered alive during their death year. Some problems explicitly state that a person is no longer alive in their death year, while others may include it. Misinterpreting this can cause subtle errors in your implementation. Carefully reviewing the problem's requirements is key. Memory usage is another challenge, especially when dealing with large year ranges. For instance, creating an array to represent every year from the earliest birth year to the latest death year might seem straightforward, but it can lead to high memory overhead if the range is vast. Instead of allocating memory for every possible year, you can use event-based processing techniques that only focus on the years with actual events. This not only saves memory but is also more efficient overall. To succeed in interviews, it's important to focus on optimizing your solution and showcasing your understanding of time complexity. For instance, when given a problem like this, think about how to reduce brute force O(y*n) complexity to something more efficient, like O(n log n), or even O(n). Sorting events or using prefix sums can help achieve this. A sweepline approach is particularly useful as it allows you to treat births as +1 events and deaths as -1 events. By sorting these events and iterating through them, you can efficiently determine the maximum population at any given time. Spotting these patterns in problems involving time intervals is a valuable skill. It's also crucial to clarify the problem's inputs and constraints up front. For example, ask whether birth and death years are inclusive or exclusive, and check if the year range is bounded. Finally, be prepared to explain how you transition from a naive approach to a more optimized one. This demonstrates your problem-solving abilities and your capacity to improve solutions under time constraints. The techniques used in the maximum population year problem are highly transferable to other interval-based problems. For instance, in LeetCode 253, Meeting Rooms 2, you use a similar event-based approach to count overlapping intervals. LeetCode 759, Employee Free Time involves finding gaps in intervals, which requires mastering interval merging techniques. LeetCode 56, Merge Intervals is another foundational problem that teaches you how to manipulate intervals effectively. Finally, LeetCode 1229, Meeting Scheduler is an interval-based problem where the focus is on finding overlapping times. Each of these problems builds on the same core concepts of sorting, merging, and counting intervals, so practicing them can significantly enhance your problem-solving skills in this domain. There are multiple approaches to solving the maximum population year problem, each with its own trade-offs. A brute force method involves iterating through every year in the range and counting how many people were alive by checking every birth and death year. While this is easy to implement, its O(y*(n) complexity makes it inefficient for large year ranges. A more optimized approach is event sorting, also known as the sweepline technique. Here, you treat births as +1 events and deaths as -1 events, sort all the events, and then iterate through them while maintaining a running count of the population. This method reduces complexity to O(n log n) due to sorting and scales well for large inputs. Alternatively, the prefix sum approach involves creating an array for the year range, incrementing at birth years, and decrementing at death years. Computing a prefix sum over this array gives the population count for each year. This method has a complexity of O(n + y), making it efficient for small year ranges, but the memory usage can become prohibitive for large year ranges. Choosing the right approach depends on the problem constraints and the input size. Great job following along. In this session, we solved the maximum population year problem by exploring multiple approaches and breaking down the solution step by step. Remember to practice similar problems to strengthen your skills. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!